Okay, so the equation that we just looked at for our gas expansion situation, we were looking at a change in work, this like infinitesimal change in work was equal to negative pressure, the exterior pressure, which was not changing, times some infinitesimal change in volume, or dV. Okay? That volume was sort of blown up on the figure so that we could see it, but we're imagining it very small. So then, and we'll look at this, in order to, if we integrate that equation over our change in volume, what we'll get is our total work is negative exterior pressure times our total volume change, or delta V, or big V, okay, our macroscopic change. So if we recall from physics, the other thing I'll say is just shout when you need me to move the paper up. Sometimes I look, sometimes I don't. Okay? Work was equal to force over distance. Force times distance, my apologies. So we can have work is equal to force times here, L will be length. Force is in newtons. Our SI unit for length is meters. And Newton meters is joules. Okay? So the SI unit for work that we'll be using is joule. Okay? It's also a unit of energy. Work is type of this energy transfer is what we're talking about. Okay? So if we want to look at the work done moving from between two positions, so if we move from position L1 to L2, we can integrate. So from position 1 to position 2, force times our infinitesimal change in length. And another way to write this, since we're interested in volume, we can multiply this through by what is essentially 1. We're going to multiply through by area over area. Okay. Integrate L1 over L2. We have force over area, A times dl. And this is just simply because A over A is equal to 1. Okay? It's like multiplying by 1, A over A. So this piece here is pressure. Force over area is pressure in newtons over meters squared. This piece here is volume. Okay? It's some cross-sectional area of whatever we're interested times length. So if we have some circle, we have a cylinder, the area of the cylinder of our piston, and then that change in length would give us our volume. Okay? The units here are meters squared times meters, or meters cubed. And so since this is essentially volume, this is essentially pressure, work is equal to, keep our negative sign for convention, because we're talking about expansion work here, going from volume 1 to volume 2, this isn't changing, the exterior times dV. Negative is sign convention. So we're talking about a constant pressure process. And what the example we're talking about now, eventually we'll get into calorimetry at a constant pressure. So protein unfolding is generally happening at a constant pressure. We talk about protein unfolding inside of the body. We're at a constant pressure, so it is nice. We also are able to consider ourselves to be isothermal. Generally, the temperature of the body is not changing significantly enough. Okay? And so we actually, when it's time to talk about real biological molecules, a lot of these assumptions, constant pressure, also called, another word for this is isobaric, okay, is a word I will use and you will see on the slides. Isobaric, isothermal, even constant volume, a protein unfolding really isn't starting to assume that much more volume, and so a lot of these sort of easy assumptions, we're at constant pressure, we're at constant volume, we're at constant temp, they actually become very relevant even when we're talking about real biological systems. Okay? So this is our gas expansion work. Okay? We're expanding against the surroundings. So if we plot pressure versus volume, pressure, here's volume, we have some constant P exterior, we have V1, some volume. We go to V2, pressure doesn't change. the work that is done is given by the area under this curve as we go from volume 1 to volume 2. This is work, but it's also negative. So we can look at work going from volume 1 to 2. This would be given by negative V1, V2, P exterior dV. We can pull the pressure out. I ran out of room. And we can write this as V2 minus V1. Okay? We're going from a bigger volume to a smaller volume. Okay? So this is just V, this is just volume. Take V2 minus V1. This is a positive term. So in this expansion case where we go to a bigger volume, a negative sign, we have a positive sign, we have negative work. Now, if we want to look at, so this is expansion work is negative. It's done, like I said, by the system. I'll probably just upload my old notes because I did a whole bunch of cute color coding. Expansion work and negative stuff's all blue, and all the compression stuff is written in red. But not this time. Too lazy to swap colors. All right, and then if we think about going the other way, so let's imagine we're at this volume here, and at constant pressure, we compress to a smaller volume. Okay. Work going from volume 2 to volume 1, keep our negative sign. Okay? Our equation always contains a negative sign. And then what we'll find is when we go from smaller to bigger, we'll get a negative sign over here. They'll cancel out, and we'll have positive work. Okay. So we have going from V1 to V2. I'm sorry, V2 to V1. P exterior dV. Negative P exterior times V1 minus V2. This is our smaller volume minus our bigger volume. This is going to have a negative sign. Okay. Negative times the negative is going to give us positive compression work. Okay. It's work done on the system by the surroundings. Okay. So if this is our system here, some box. Like I said, it's almost always a cylinder, but maybe sometimes I'll make it a square. Who knows? Okay. So we have, for expansion work, we've increased our volume here. We expanded up against. Our surroundings are just everything out here. System. And this difference here, this change was our change in length times our cross-sectional area, or a change in volume. Whereas for compression, we have some piston and our piston cylinder set up. This is our compression work. So in this situation, we've only considered, if we can see all of that, we've only considered a constant pressure situation. We can also think about, we're no longer interested in constant pressure. Pressure can change, but what about if volume can't change? So what does a pressure volume plot look like for the isovolumetric, also called isochoric situation? We have some volume V. It doesn't change. Okay, so this is a scenario where I have some sort of reaction in my piston cylinder, and I'm holding the cylinder. The piston is still. It can't move. Okay, it's fixed in place. I have some stoppers there. And so the gas wants to expand against it. It can't. Okay, so rather than being able to change its volume, the pressure will go up, okay, inside that constant volume cylinder. But what is the work for this situation? 0. How do you know? Can't integrate under a vertical line. Okay? Work is equal to 0, okay? Because trying to integrate under this vertical line would give 0 work. So in an isovolumetric or an isochoric process, no work is done. Work requires this movement, this change. The piston's got to move across a distance in our piston cylinder case, which you'll definitely get a question or two about.